In this question here, we want to find the magnitude of the radius of curvature at the point x equals 1 on the curve C, which has the equation y equals arctangent of 3x. Now, the radius of curvature in differential geometry is given as the absolute value of rho, so that's the Greek letter rho, and what that equals is we've got a ratio here. Now on the bottom of the ratio, the denominator, we've got the second derivative, so d squared y dx squared, and in the numerator what we have is we have 1 plus the first derivative, of which the first derivative is squared, and then all of this numerator is cubed and then taken the square root of. That's the formula for the absolute value of rho. So with that, we have to take the absolute value of this side as well. So because it's a magnitude, we don't want any negative values. Magnitude is always positive. So we've got a few things in here that we need to take care of first before we can start calculating the answer to this. Now we've got the first derivative here, and we've got the second derivative here. So let's find the first derivative of this. So let's go down here. So dy dx, that's the first derivative. Now here we've got a constant multiple of 5, and the arctangent, now there's a standard derivative of that when we've got 3x. What that is for example arctangent 3x, so the derivative with respect to x of inverse tangent of ax, let's just write this in here, ax. What that gives us is a over a squared x squared plus 1. That's what we get. So for this one, with the arctangent of 3x, what we've got here, our a value is 3, so that's 5 times 3, and we divide it by a squared, which is 9, x squared, and then plus 1. So that's the result of our first derivative, and the numerator 5 times 3, that just becomes 15. So that's our first derivative. Now we need to find the second derivative. So d squared y dx squared, that's the second derivative. So basically the derivative of this. Now we could rewrite this as 15 times 9x squared plus 1 to the minus 1. Now that's slightly easier to work with. That certainly works for me. So what we do here now, using the chain rule, minus 1 times 15, so that gives us minus 15. Input stays as it is, 9x squared plus 1. I'm going to leave a little gap here because we need to implement the chain rule. And then take the derivative of the inside, which is 18x. So minus 15 times 18x. And then drop the power by 1, gives us minus 2. Now we can rewrite this in this kind of format. Minus 15 times 18x is minus 270 times x. And then over 9x squared plus 1, which is all squared. So that's our second derivative. So now we've got the building blocks for what we can put in here. So now we need to calculate this at the value where x equals 1. So what we want now is, next we want dy dx at the value 1. So that, if we plug in 1 into this, we're going to get 15 over 9 times 1 squared plus 1. So that gives us 15 over 10, which equals 3 over 2. So that's our value of the first derivative at x equals 1. Now we need the second derivative also at the value where x equals 1. So now x equals 1, we've got minus 270. And this time we've got 9x squared plus 1. So again, this denominator inside the brackets is 10. Square that, we get over 100. So that becomes minus 2.7. And this one here becomes 1.5. Okay, so now we can got all our building blocks together. We can plug those into our formula for the value of rho. So that's our first lot of calculations. This is our derivative calculations. So let's keep these all separate. Now let's go on to this one. So the absolute value of rho gives us the absolute value. Now we've got 1 plus the first derivative squared. Now we've got the first derivative here as 1.5. Now we can square that, no problem. 15 15s are 225. So move the decimal point back 2 places, 2.25. So now we've got 1 plus 2.25. And then that's the power of 3 over 2. And then we divide that by the second derivative, which is minus 2.7. Okay, now bearing in mind this bit doesn't include our denominator. Okay, so now the absolute value of rho is the absolute value of this thing on the numerator divided by minus 2.7. Now, if we plug that into a calculator, we're going to get something around about 2.17. So minus 2.17. Now, if you take the absolute value of that, that's just going to give me 2.17. Now, bear in mind, this is to 3 significant figures. So therefore, our magnitude for the radius of curvature, which is Greek letter rho, that equals 2.17 to 3 significant figures. And that is our answer. Let me just put that in there, nice little box. Okay.